Welcome back to the Deep Dive, where we unpack the most fascinating research, extract those surprising nuggets of knowledge, and give you a shortcut to being truly well-informed. Today we're diving into an idea that sounds almost like science fiction. Imagine a tiny computer, perhaps nestled inside your smartwatch or a smart speaker, that can understand your voice, anticipate your movements, and do it all with less power than a single LED light bulb.
It sounds incredible, doesn't it?
It really does. And here's the kicker. It does this right on your device, without ever needing to send your sensitive data scurrying off to the cloud. What if we could imbue our everyday smart devices with the cognitive power of a brain, but, in a package so small and energy efficient it's practically invisible?
Well, that's moving from science fiction towards reality.
Exactly. That's not just a dream for the future. It's precisely what groundbreaking research from the Indian Institute of Science at Bangalore is making a reality. We're zeroing in on a remarkable paper today. It's titled Neuromorphic Time Multiplexed Reservoir Computing with On-the-Fly Weight Generation for Edge Devices. Quite a mouthful, but the authors are Sarthak Gupta, Satyajit Chakrabarty, and Chetan Singh Thakur.
And it's truly fascinating work in the neuromorphic space.
Our mission today is to demystify how these brilliant researchers are drawing profound inspiration from the ultimate biological computer, the human brain. I mean, think about it. Our brains perform these incredibly complex tasks like audiovisual perception, recognizing a friend's voice in a noisy room, or seamlessly detecting objects around us, all while consuming a mere 20 watts of power.
20 watts. It's astonishing.
Less than most light bulbs. So we'll explore how they're harnessing that brain-like efficiency to forge incredibly powerful yet incredibly low-power hardware for artificial intelligence. And crucially, right on the edge, meaning on your device where it matters most.
That edge component is key.
For you, the listener, this translates to faster, more private, and ultimately far more powerful smart devices. We'll explore the critical why behind this effort, the ingenious how of their neuromorphic hardware architecture, and of course the transformative what it means for everything from instantly recognizing your speech to understanding human activity in real time.
It's truly a pivotal moment, I think, in the evolution of AI, especially for these constrained environments. This research really represents a fundamental shift in how we might design computation for the next generation of truly intelligent devices we interact with daily.
Okay, let's unpack this incredible concept of brain-like efficiency right from the very beginning. When we talk about the human brain, we're marveling at an organ that handles just a staggering array of complex cognitive tasks. Just take a moment to consider it. Your brain effortlessly recognizes different dialects and accents, maintains your attention, stores and retrieves vast memories, and coordinates every intricate motor command you make. Like picking up a cup.
Effortlessly, from our perspective. Inside, it's a whirlwind of activity.
Right, all these incredibly sophisticated processes running simultaneously on a mere 20 watts. Seriously, that's less power than the typical light bulb illuminating your room right now. It's an astonishing testament to biological engineering, isn't it?
It genuinely is. And what's truly fascinating here, if we contrast it with our traditional silicon-based computers, is the sheer efficiency gap. Our biological systems comprised of neurons that are comparatively slow, actually, and inherently stochastic, meaning they fire with a degree of randomness.
Right, not perfectly predictable.
Not at all. They still manage to outperform today's most powerful, energy-hungry supercomputers in many real-world dynamic tasks, especially in areas like vision and audition, where the real world throws a constant barrage of noisy, ambiguous, and rapidly changing information at us.
Yeah, the real world isn't clean data.
Exactly. Our brains possess a level of adaptability and energy efficiency that even our most advanced machines struggle to match. This ultra-low power characteristic of our own wetware is, without exaggeration, the holy grail for designing next-generation electronic devices, particularly those that need to be always on, always aware, and always ready to respond without constantly needing to be tethered to a power outlet or a huge battery.
So the brain is clearly our ultimate benchmark for efficiency.
Yeah.
But then we hit this wall, this sort of PPA wall you mentioned, with traditional computers, when we try to put that kind of power into a tiny device. This leads us to edge computing. Why is putting intelligence at the edge right on your device, whether it's a smartwatch, a smart speaker, maybe a specialized medical sensor, or even something in your car? Why is that such a significant priority right now? Why not just continue sending all that data to a powerful cloud server like we often do?
That's a crucial distinction, and it's becoming more important every day. Edge computing is all about processing data at its source, or as close to the point of generation as physically possible. If we connect this to the bigger picture, this offers immense, almost transformative advantages across a huge spectrum of applications. Firstly, it drastically lowers bandwidth requirements. Think about it.
Less data flying around.
Precisely. Instead of sending gigabytes of raw sensor data, say video or continuous audio to the cloud, you're only sending small pre-processed insights, or maybe sometimes nothing at all if the decision is made locally. This means less strain on your home Wi-Fi, less load on cellular networks, and faster communication overall when it is needed.
Okay, that makes sense. Bandwidth. What else?
Secondly, and this is becoming increasingly important, I think, for everyone, it significantly enhances data integrity and, critically, user privacy. Sensitive information, be it your biometric data from a health tracker or your voice commands to a smart assistant, can remain entirely on your device.
So it never leaves your personal space.
Exactly, mitigating many privacy concerns and potential security risks, and perhaps most importantly for real-time applications, it offers significantly lower latency.
Ah, the speed factor. No round trip to the cloud and back.
Right. Imagine instant, seamless responses from your voice assistant or immediate detection of a critical medical anomaly from a wearable sensor without any internet delays whatsoever. The thinking happens right there.
Okay, faster, more private, less data hogging. Sounds great.
But, and this is the big but, this raises an important question. If it's so good, what has limited complex computation at the source until now? Why haven't we always done this? The primary constraints, especially for tiny battery-powered devices, boil down to what we call PPA, power, performance, and area.
Power, performance, area. The classic chip design constraints.
Exactly. Traditional computational methods, particularly for sophisticated AI algorithms like deep neural networks, demand a lot of power. They require substantial memory to store models and intermediate data, and consequently need a larger physical footprint on the chip. These quickly hit the PPA limits, making them unsuitable for the compact, energy-constrained form factors of modern edge devices.
You simply can't cram a data center into a hearing aid.
Precisely, or run it on a coin cell battery for a year.
So the core challenge is crystal clear. How do we marry the brain's incredible efficiency and intelligence with the tiny, power-constrained realities of edge devices? How do we build something that can think with brain-like sophistication but sips power like a hummingbird? This is where this paper introduces a neuromorphic computing paradigm. That sounds incredibly sci-fi, almost futuristic, but what exactly is that in the context of this research? How does it help solve this monumental challenge?
It's a truly fascinating and foundational concept, and maybe less sci-fi than you might think. Neuromorphic computing is a fundamentally new approach to computation. It draws direct, explicit inspiration from neurobiological systems, essentially, from how our brains are wired and how they operate.
So copying the brain structure, not just trying to get the same result.
In essence, yes. Instead of the traditional sequential von Neumann architecture, which famously shuttles data back and forth between a separate processing unit, and memory, the von Neumann bottleneck.
Right, that data transfer costs energy and time.
A lot of it. Neuromorphic computing strives to mimic the brain's parallel, distributed, and highly efficient processing, often by co-locating memory and processing, much like synapses and neurons. It's not just a slight optimization of existing computer design, it's a fundamental reimagining. Think of it as building a computer that behaves more like a network of interconnected neurons rather than a series of logical gates processing instructions sequentially.
A different way of thinking about computing itself.
Exactly. It's a wonderfully cross-disciplinary field, leveraging deep insights from neuroscience, computer science, electronics engineering, mathematics, all collaborating to build systems that learn and process information much more like living organisms do.
That makes a lot of sense, trying to replicate the brain's architecture for efficiency. And within this broad, brain-inspired field of neuromorphic computing, the paper specifically highlights reservoir computing. Is this a brand new type of AI or something more specialized within the neural network family tree?
Reservoir computing, or RC, is indeed a very powerful and, I'd say, elegant type of recurrent neural network, often abbreviated as RNN. To grasp its significance, it's important to remember that recurrent pathways where information loops back on itself, creating internal state or memory, are a fundamental aspect of biological systems.
Our brains rely heavily on feedback.
Absolutely. Our brains are full of feedback loops, allowing them to process sequences, understand context over time, and build internal models of the world. RNNs are mathematically excellent at modeling these kinds of dynamic systems and processing temporal data.
like speech or video or movement patterns over time.
Exactly, things that unfold sequentially. However, traditional RNNs, while powerful, have a notorious drawback. They're incredibly difficult and computationally expensive to train. They suffer from issues like very long training times and complex mathematical problems such as vanishing or exploding gradients.
Ah, yes, the gradient problems that plagued early deep learning.
Right. These can make RNNs unstable and incredibly challenging to optimize reliably, especially for complex long sequences. This is where RC emerged as a particularly brilliant and powerful alternative, especially attractive for hardware implementation due to its simplicity. Its core strength lies in its profound simplicity, almost a less is more approach. In RC models, specifically the echo state network, or ESN, which this paper focuses on, the input layer connects to a reservoir, a network of interconnected nodes, like a simulated pool of neurons. The crucial insight is that the weights for these connections, both from the input layer to the reservoir and the internal, usually sparse connections within the reservoir itself, are generated randomly. Yes, randomly initialized within certain constraints, and then they are fixed. They don't change at all during the learning phase.
Wait, they stay random? That sounds completely counterintuitive for an AI system that's supposed to learn. How does anything get learned if the core network is just random and fixed?
It does sound odd at first, doesn't it? But that's precisely the ingenuity and the source of RC's efficiency. Think of the reservoir as a complex, fixed, high-dimensional dynamic system. Like dropping a pebble into a pond, the input creates a rich, complex pattern of ripples or echoes within this fixed reservoir. Because the reservoir has recurrent connections and nonlinear dynamics, even simple inputs can generate very complex, unique temporal patterns of activation within it.
Okay, so the reservoir creates complex patterns based on the input.
Exactly. And the learning part, only the readout weights. These are the connections from this fixed reservoir to the final output layer are trained.
Ah, so you just train the interpretation of the ripple pattern, not the pond itself.
That's a perfect analogy. You train a simple linear layer, basically, to read these complex internal states generated by the reservoir and map them to the desired output classification. This vastly simplifies the entire training process. Instead of needing complex, computationally intensive backpropagation algorithms that adjust potentially millions of weights throughout the network, you can use much simpler and significantly faster linear regression techniques or similar methods to determine just those readout weights.
So training becomes incredibly fast and cheap, computationally speaking.
Orders of magnitude faster and more efficient to train and deploy. This makes RC extremely well-suited for complex temporal data classification tasks common at the edge, like understanding speech patterns or recognizing human activities from sensor data. Now, the paper does describe this process with a few core equations, equations 1 through 5, if you're looking at it. But without getting lost in the mathematical notation, which isn't great for audio, what these equations essentially describe is how each tiny part of this brain, each node in the reservoir, takes in new information from the input, how it remembers what happened just before within the network through those recurrent connections, and then uses that combined understanding passed through an activation function like tan to produce an output state. The final classification is then just a weighted sum of these reservoir states, using those trained readout weights.
So input complex fixed dynamics, learnable interpretation.
Precisely. The training just involves finding the best weights for that final interpretation step, typically by minimizing a simple error function using linear methods. It's elegant because the complexity is in the fixed dynamics, not the learning process. They also mention using metrics like kernel rank and generalization rank to analyze the quality of this fixed reservoir, ensuring it can effectively distinguish patterns, generalize, and remember past info.
That's a fantastic insight into why reservoir computing is so attractive for efficiency. But here's where, as you said, it gets really interesting because the researchers didn't just implement standard RC. They made some truly clever, almost ingenious modifications to make it genuinely suitable for the extremely tight constraints of edge devices. What were these core innovations that really set this work apart from, say, just running a standard RC model on a chip?
That's absolutely right. This wasn't just implementing RC, it was re-engineering RC for the edge. The first major innovation, and it's quite intuitive when you think about how our own brains are somewhat modular, is how they handle the sheer size of the reservoir needed for complex tasks. Imagine trying to build a chip that perfectly mimics a large, complex brain region. That'd be huge and power-hungry. Instead of attempting to build one massive, monolithic, and inevitably power-hungry chip to emulate a large reservoir, say, one with 3,200 nodes, as in their examples, this design proposes splitting that large conceptual reservoir into many smaller, more manageable, configurable reservoirs.
Okay, breaking it down.
Right. They might, for instance, configure it as 100 smaller reservoirs, each with only 32 nodes.
So it's like having a team of specialized mini-brains or mini-processing units instead of one giant, power-hungry superbrain. That makes a lot of sense for efficiency and maybe even specialization.
Exactly, like parallel processing with smaller units. And the trick doesn't stop there, which is truly brilliant from a hardware perspective. They don't actually build 100 separate physical mini brains or reservoir blocks on the FPGA. That would still take up considerable area.
Ah, okay. So how do they get 100?
Instead, they build one single, small, configurable reservoir block and then ingeniously reuse it multiple times over a very short period using a technique called time multiplexing.
Reusing the same hardware block over and over very quickly.
Precisely, because the FPGA, the field programmable gate array where this system is implemented, runs at clock speeds of tens to hundreds of megahertz, which is orders of magnitude faster than typical sensor sampling rates. Sensor data might come in at only tens of hertz, maybe a few kilohertz for audio.
So the chip has loads of spare time between sensor readings.
Loads of it. So the single small physical block can be reconfigured and process different virtual reservoirs sequentially using the same input data buffered in RAM. From the system's perspective, and in terms of the final computation, it appears as if multiple distinct reservoirs are working simultaneously or in parallel. This drastically minimizes hardware resource utilization, fewer logic elements, fewer registers, a much smaller physical footprint, and significantly lower power consumption because you're only powering that one small block intensely.
Wow, okay. That's like having a single, incredibly skilled chef who can cook 100 different dishes one after another so fast that it seems like 100 chefs are working simultaneously.
That's a great analogy. It's a brilliant hardware hack for tiny devices.
Okay, so that's innovation one, time multiplexed mini reservoirs. What's the second big one?
The second core innovation is equally critical for resource-constrained edge devices, the on-the-fly generation of binary weights and connectivity.
On-the-fly generation. That sounds like a massive memory saver. Instead of storing all those intricate connection weights, which, as you said, could be millions of values in a large network, the system essentially generates them as needed, like pulling them out of thin air.
You've absolutely hit on the core advantage, and it's a potential game changer for memory, which is often a huge bottleneck in edge AI. Conventional RNNs and even many other reservoir computing implementations require significant amounts of memory, often power-hungry external DRAM, just to store all their connection weights.
Right, no model parameter.
Exactly. This proposed design, however, generates the sparse reservoir connectivity pattern, along with both the feed-forward weights from input to reservoir and the recurrent reservoir weights within the reservoir. It generates them on the fly using a very efficient technique based on a linear feedback shift register, or LFSR.
An LFSR, like the things used for pseudo-random number generation.
Precisely. LFSRs are very simple, low-resource circuits that can generate long sequences of pseudo-random bits from a small initial seed value. So the implications of this are enormous for edge devices. Instead of needing to store potentially millions of complex floating point or even fixed point weight values, you only need to store the small initial seed value of the LFSR for each virtual reservoir. That's a tiny amount of data.
So the memory footprint plummets.
Dramatically. And crucially, it significantly reduces memory read operations during computation because you're generating the weights locally instead of constantly fetching them from memory. The paper explicitly highlights how power-intensive memory access is. For context, they state a single DRAM access can consume thousands of times more power than an 8-bit multiplication.
Thousands of times, wow.
Yeah, and even on-chip SRAM access consumes tens of times more. By almost eliminating these constant power-hungry memory reads for the reservoir weights, they achieve truly massive power savings.
It's like not needing a giant cookbook because you can instantly conjure up the recipe word by word as you cook.
Another excellent analogy. You just need the starting idea, the seed.
And I noticed you mentioned the weights are binary, not just generated on the fly, but binary. What does that mean for the actual math and computation happening on the chip? Does it simplify things even further?
It absolutely does, and it's another brilliant move towards extreme efficiency, pushing the PPA optimization further. By simplifying the feed-forward and recurrent reservoir weights to just binary values, that is, literally just a +1 or a -1, they completely eliminate the need for computationally expensive multiplication operations when determining the reservoir states.
No multipliers needed for the main reservoir calculation.
Correct. Multipliers are typically significant consumers of power and chip area, especially if you need many of them working in parallel. Instead, the hardware only needs simple adders and subtractors. If the weight is +1, you add the input. If it's -1, you subtract it.
Much simpler logic.
Much simpler. This dramatically reduces the logical resource utilization on the FPGA. Fewer logic elements, fewer dedicated multiplier blocks are required. The result is an optimal power, performance, and area PPA design. It's precisely what's needed for resource-constrained edge devices where every microwatt and every square millimeter counts. It's like instead of doing complex algebra, the system only has to do basic addition and subtraction, but it does it incredibly fast and efficiently.
Okay, so we have this ultra-efficient, brain-like classifier. It uses time multiplexing for hardware reuse and generates its own binary weights on the fly to save memory and power, doing calculations with just add, subtract. But how does it actually see or hear the world around it? How does it get its sensory input, its raw data, before it can start doing its clever processing with those reservoirs?
That's a great question because the classifier is only as good as the information it receives. Feature extraction is the crucial first step in any effective AI system, acting as the interface to the real world. It's all about taking raw, often noisy, high-dimensional input data, whether it's sound waves from a microphone or accelerometer readings from a motion sensor, and pulling out the most useful, salient information for the classifier to work with.
Kind of like pre-processing the data into a more useful format.
Exactly. Think of it as giving the system its senses and then interpreting those raw senses into a more structured language. The AI core, the reservoir system in this case, can understand and process effectively. And the specific method of feature extraction naturally varies depending on the type of data the system is designed to process.
So what do they use for audio, for speech recognition?
For auditory data, like the speech commands in the Digits dataset, they employed a highly sophisticated and biologically inspired neuromorphic cochlea model. It's called CARFAC. CARFAC stands for Cascaded Asymmetric Resonators Fast-Acting Compression. What's truly remarkable about this model is that it's directly inspired by and meticulously mimics the function of the human cochlea, the spiral part of your inner ear. It models the early and mid-auditory processing stages that happen within our own ears, including the mechanics of the basilar membrane, the amplification effects of the outer hair cells, and the signal transduction by the inner hair cells.
So it's literally mimicking how our ears physically process sound frequencies before this brain-like classifier even gets the data. That's incredible, like building a digital front-end ear.
Precisely. It's neuromorphic sensing feeding into neuromorphic processing. When sound waves enter your ear, they travel to the cochlea. Inside, the basilar membrane, or BM, vibrates at different locations in response to different sound frequencies.
The tonotopic map, right? High frequencies at one end, low at the other.
Exactly that. It creates this frequency map. The inner hair cells then convert these mechanical vibrations into electrical nerve signals. The CARFAC model computationally replicates this. It processes the simulated basilar membrane output through steps like half-wave rectification, sort of like only keeping the positive part of the signal, mimicking how neurons fire, and then uses a series of filters and compression stages, essentially extracting the energy corresponding to each frequency channel over short time windows.
So you get a time-frequency representation, like a spectrogram, but generated in a way that mirrors biology.
A very biologically plausible time-frequency representation, yes. The outputs of these CARFAC resonators, which are essentially a detailed frequency-energy fingerprint of the sound evolving over time, are then fed directly into their time-multiplexed reservoir classifier. This biologically inspired front end is incredibly effective at capturing the most salient features of sound, especially speech, in a way that's robust to noise, just like your own ear does.
Fascinating. Okay, so that's the ear. What about for human activity recognition, the HAR task? How does it sense movement?
For HAR tasks like detecting if you're walking, jogging, standing still, based on data perhaps from a smartwatch or a smartphone clipped to your waist, the input data is typically from a multi-axis accelerometer. The process here begins by taking this raw accelerometer data, usually XYZ axis, and cleverly segregating it into body acceleration, the actual movement and gravity acceleration, the constant downward pull.
Separating intentional movement from just the phone's orientation relative to gravity.
Exactly. This is important for consistency. Then, instead of a complex model like CARFAC, they calculate a set of well-established time-domain statistical features for the separated acceleration components within overlapping time windows. These aren't just raw acceleration numbers, they are powerful statistical summaries that describe the nature of the movement within that specific window.
What kind of statistics?
Things you might recognize: the mean, average acceleration; the median, middle value, robust to spikes; standard deviation, spread of acceleration values; root mean square, magnitude of acceleration. They also include features like skewness, asymmetry of the movement pattern, interquartile range, another measure of spread, and the maximum and minimum acceleration values detected within that window.
So capturing the intensity, variability, and shape of the movement pattern statistically.
Precisely. These statistical descriptors are highly effective at capturing the unique signatures of different human activities. Walking has a different statistical pattern than jogging or sitting, in a very compact, meaningful way, ready for the reservoir classifier.
That's a truly clear picture of how the system gets its senses, either hearing like a digital ear or detecting movement patterns through statistics. Now, you've mentioned this entire incredibly complex neuromorphic system is implemented on an FPGA. Can you walk us through the high-level workflow? Give us a glimpse inside how this brain-like chip actually operates day to day, or millisecond to millisecond. What does the process look like from raw sensor data hitting it to a final classification decision coming out?
Absolutely. Let's trace the data flow. The proposed system, prototyped on an Intel Cyclone 10 low-power series FPGA, chosen specifically for its low power consumption, is designed to be always on, but in a very smart, energy-efficient way. It's not constantly crunching numbers at full tilt. Instead, it continuously monitors the incoming raw sensor data stream using a simple detector circuit looking for what they call onset activity.
Waiting for something interesting to happen.
Essentially, yes. For example, it's patiently listening for the distinct acoustic signature that indicates someone has started speaking, or it's watching the accelerometer for the telltale patterns of someone beginning to move purposefully rather than just random jitter.
So it only wakes up the main processing when needed. Power saving again.
Exactly. Once that onset activity is reliably detected, a crucial power-saving step, an internal trigger signal, is activated. This trigger initiates the sampling and temporary storage of the raw sensor data for a fixed interval, capturing the event of interest, like a spoken word or a few seconds of walking. Crucially, as this data is being captured or immediately after, it's simultaneously fed into and processed by the feature extraction block, which, as we just discussed, is either the neuromorphic Carfax cochlear model for audio or the statistical feature calculator for HAR.
Okay, data comes in, gets feature extracted. Then what?
The extracted features those rich, compressed summaries like the Carfax output or the statistical movement descriptors are then temporarily stored in a small on-chip RAM block.
Why RAM? Why not feed them straight to the reservoir?
Because of the time multiplexing. Remember, our clever split reservoir classifier needs to reconfigure and reuse the same physical reservoir hardware module multiple times to simulate all the different virtual reservoirs. To do this fairly, each virtual reservoir needs to process the exact same extracted features from that time window. So the features are stored in RAM momentarily so they can be read out repeatedly as the hardware block reconfigures itself for each virtual reservoir pass.
Got it. The features wait in RAM while the single hardware block pretends to be many different reservoirs in quick succession.
Precisely.
Yeah.
A set of internal control signals, the paper mentions signals like restart, reservoir, and window, manage this intricate process. They act like a tiny conductor orchestrating this mini orchestra of processing. The restart signal ensures the reservoir module's internal state is cleared before processing a new chunk of data. The reservoir signal tells the module which virtual reservoir it's currently is emulating, triggering the loading of the correct LFSR seed. And the window signal then feeds the appropriate feature data points for the current time window from the RAM into the now configured reservoir module sequentially. After all feature points from a specific time window are fed through, a certain number of delay clock cycles are allowed. This is for the crucial recurrent operations to take place within the reservoir.
Letting the internal echoes develop.
Exactly. Allowing the reservoir's internal state to update itself based on its previous activity, which gives it that essential memory or context over time.
That's a fantastic analogy. A conductor orchestrating a highly efficient, multi-purpose orchestra playing from the same sheet music stored in RAM. And what's happening inside that dynamically configurable reservoir module itself during each pass? How does it actually crunch those numbers with all these on-the-fly binary weights and make the classification decision?
Right, let's zoom into that core configurable block. Inside it, small read-only memory, or ROM, blocks are used. These store the essential static information that doesn't change on the fly. This includes the trained readout weights, learned offline, any bias values for the output nodes, and critically, the initial LFSR seed values a different seed for each virtual reservoir it needs to emulate.
So the seeds are stored, but not the millions of weights they generate.
Correct. When a pass begins for a specific virtual reservoir, its corresponding seed is loaded into the LFSR circuit. The LFSR then springs into action, acting as that dynamic weight generator we discussed. It instantly conjures up the required binary, plus one-to-one feed-forward weights for the incoming features, the binary recurrent weights for the internal connections, and even the addresses for where those sparse recurrent connections should go, all generated dynamically from the seed. So each clock cycle within the processing window, a feature data point from the RAM, and its corresponding dynamically generated binary feed-forward weight are fed into all the reservoir nodes or accumulators in parallel. The value in each node's internal accumulator is then simply updated by either adding or subtracting the feature value, based on whether that binary weight was a +1 or a -1. Remember, no multipliers here.
Just add or subtract based on the fly generated weights. Yeah. Super efficient.
Extremely efficient. After all the input feature points for a given time window have been processed in feed-forward manner, the recurrent feedback process begins. In this stage, the previous output values, or states, of the reservoir nodes themselves, combined with their dynamically generated binary recurrent wakes from the LFSR, are fed back as new inputs to the nodes. Again, just additions and subtractions.
That's the internal feedback loop, the echo mechanism.
Exactly. This internal feedback is what gives the reservoir its memory and its ability to capture dynamic, time-sensitive patterns. Finally, after these recurrent operations complete for the window, a nonlinear activation function is applied to the accumulated values in each reservoir node. The paper details using a piecewise linear approximation of the standard hyperbolic tangent tan function. This is clever because tan is common in RNNs, but approximating it with linear segments can be implemented very efficiently using just bit shift operations and additions on an FPGA. Again, avoiding complex math.
More efficiency tricks.
Right. The results from this activation function, the final state of the reservoir nodes for that window, are then multiplied by the learned readout weights, which were loaded from ROM. And notably, the paper mentions that even the few multipliers needed for this final readout step are also time multiplexed to further save hardware resources.
Wow, they really squeezed every bit of efficiency out.
They really did. Biases are added to these outputs, and eventually an outvalid signal is triggered. This indicates that the final outputs for each possible class are ready in the output accumulators. The predicted classification label is then simply the class corresponding to the output node with the maximum accumulated value. This entire intricate sequence is meticulously orchestrated to process sensor data with minimal power, minimal memory footprint, and maximum hardware resource reuse.
So what does this all mean in the end? We've built this incredibly intricate, biologically inspired system on a chip. It uses time multiplexing, on-the-fly binary weights, adder-based computation, neuromorphic sensing. But how well does it actually perform in the real world when put to the test? Does all that incredible efficiency come at a huge cost to accuracy? Is it actually usable?
This is absolutely the crucial question. The proof is in the pudding, as they say. And the results presented in the paper are genuinely compelling, highlighting the power and practicality of their design philosophy. Let's look at speech recognition first. They validated their system on the well-known T-digits dataset. This dataset includes recordings of people speaking digits from 0 to 9, plus the word O. They used a substantial number of samples, 2,464 audio files for training the readout weights, and 2,486 different files for testing. All the audio was downsampled to 8 kHz, focusing on the frequency range most important for human speech intelligibility.
Okay, standard data set, good amount of data. What metric did they use?
The primary performance metric for speech is typically word error rate, or WER. A lower WER is better, meaning fewer words were misidentified by the system. What's particularly insightful in the results is how they meticulously analyzed the trade-offs involved in their architectural choices. It wasn't just about one final number.
Exploring the design space.
Exactly. For instance, they looked at the impact of the number of virtual reservoirs. When they increased the number of 32 node reservoirs from 100, totaling 3,200 virtual nodes, to 200, totaling 6,400 nodes, the word error rate only improved by a small amount, about 0.5%. However, this minor accuracy bump came at the direct cost of doubling the memory required for seeds and readout weights, and significantly doubling the processing latency because the hardware block had to be reused twice as many times.
So diminishing returns on accuracy, but linear cost increase.
Precisely. So after careful analysis, they concluded that 100 reservoirs, totaling 3,200 virtual nodes, offered the optimal balance of accuracy, memory, and latency for this specific task. It's about finding that sweet spot.
Makes sense. You don't always need the absolute best accuracy if it means your device battery dies in an hour.
Exactly. They also explored reducing the number of nodes per reservoir, going from 32 nodes down to 16 nodes. Now, this successfully halved the hardware resource utilization for that core configurable block, making the chip design potentially even smaller and lower power per computation step. However, this reduction came with a performance trade-off. The WDR increased by approximately 1.3%, and again, the latency doubled.
Why did the latency double there?
Because to achieve the same total number of virtual nodes, say 3,200, if each reservoir only has 16 nodes, you need to run the time multiplexing process 200 times instead of 100 times. So the single configurable block was reused twice as often.
More sequential steps. Got it. So clear knobs to turn based on the desired balance between accuracy, speed, size, and power.
Absolutely.
Yeah.
And the key comparison. They ultimately compared their final fixed-point, binary-weighted, on-the-fly generated architecture, specifically using a configuration of 200 reservoirs of 16 nodes each, still 3,200 total nodes, to a conventional floating-point 3,200-node reservoir simulation, which represents a more standard software approach.
Right.
The result, their highly optimized hardware architecture had a WDR that was approximately 2.3% higher than the ideal floating-point version.
Okay, so about a 2-3% hit in accuracy.
Yes, and that 2.3% is essentially the accuracy cost they consciously paid to achieve the truly massive efficiency gains in power, memory, and hardware resources. That's the core trade-off.
This seems like a potentially very worthwhile trade-off for many edge applications. What about the human activity recognition? How did it do there?
For the HAR task, which was tested on data collected from both wrist-worn accelerometers and waist-mounted smartphones, the system also performed admirably. The paper includes confusion matrices, which are visual grids showing how often the system correctly classified each activity, like walking, jogging, standing, sitting, versus how often it confused one activity for another. These matrices show a strong diagonal line indicating high accuracy, with relatively few misclassifications in the off-diagonal cells. It clearly distinguishes between the different activities well.
And how does this HAR performance stack up against other existing approaches, maybe ones that aren't using this specific neuromorphic hardware? Is it just efficient, or is it genuinely competitive in terms of getting the answers right?
This is another really important finding. What's truly fascinating here is that their proposed fixed-point, hardware-friendly architecture achieved comparable performance, meaning similar accuracy levels, to a range of existing software methods reported in the literature of the same or similar HAR tasks. These software methods include computationally much more complex and resource-intensive algorithms like random forests, RF, sophisticated recurrent networks like long short-term memory networks, LSTMs, powerful convolutional neural networks, CNNs, and standard machine learning techniques like support vector machines, SVMs.
So it's holding its own against algorithms that often require much more computational power.
Yes. This is a truly significant achievement because it validates that the extensive hardware-level optimizations and the efficiency-driven design choices they made, like binary weights and time multiplexing, didn't necessarily lead to a huge sacrifice in classification accuracy for this type of task. It demonstrates that they've potentially found a highly viable, high-performance solution for edge AI that genuinely respects the stringent physical constraints of the target devices.
Okay, this is where the core value proposition of this research truly shines, isn't it? The numbers behind the unbelievable power and memory savings. This is what makes it so potentially revolutionary for you, the listener, and the future devices you might use.
Absolutely. This is the centerpiece of their innovation and, frankly, what makes this work so transformative for the field of edge AI. Let's talk numbers. The memory required for storing just the essential parameters in their system, the LFSR seed values, the biases, and the trained readout weights, is incredibly small. For one configuration, they report needing just 34.9 kilobytes for 8-bit readout weights.
Kilobytes, not megabytes or gigabytes.
Exactly. To put that in perspective, that's less than the size of a typical small digital photo or a short text document. It's tiny. Based on their analysis and comparisons, they achieved an order of magnitude reduction that's roughly 10 times less in both power consumption and memory requirements compared to previously published FPGA models designed for speech recognition tasks of similar complexity.
An order of magnitude is huge in hardware design.
It's enormous. To give you some concrete power numbers they reported from their validation on a Xilinx Sync platform, the proposed design consumed only 0.155 watts during operation. Now, compare that to existing FPGA-based works they cited for similar tasks, which consumed 1.65 watts or even 1.827 watts.
Wow, that's like 10, 12 times less power.
Exactly, a truly massive reduction. It's the difference between a device needing constant charging versus potentially running for days or weeks on a small battery. And this substantial decrease in power consumption is largely attributed to two key factors we discussed. First, the computational efficiency of using binary weights and adder-subtractors instead of multipliers. And second, the minuscule memory footprint. Because the model is so small, all the necessary parameters, seeds, biases, readouts, fit comfortably within the FPGA's own internal on-chip memory, like block RAMs and registers.
So no need for external RAM chips.
Precisely. This completely eliminates the need for power-hungry off-chip DRAM access, which those existing works often require just to store their larger models. That DRAM access, as we noted, is a major power hog. Furthermore, they state the number of parameters that need to be stored is less than 150 times compared to some existing works.
150 times fewer parameters.
It underlines the revolutionary efficiency of their approach. Imagine your smart speaker. Instead of needing to be plugged in constantly, maybe only needing a charge once every few months for its basic wake word detection and simple command processing, that's the kind of leap this technology could enable.
Mind-blowing savings. What about speed? Latency?
Yes, beyond power and memory, the proposed work also achieves significantly lower latency per process time window. This is absolutely critical for real-time applications where quick responses are paramount for a good user experience. What's even more impressive is that they achieved this lower latency even when their FPGA implementation was running at less than half the clock speed of some of the existing competing designs they compared against.
Faster results, even with a slower clock. How?
It speaks to the inherent efficiency of the architecture. Fewer, simpler operations per step, and no bottlenecks waiting for external memory access. For example, they report that processing a 750 millisecond audio sample, which they broke down into 45 overlapping time windows, takes only 23.6 milliseconds on their system.
Less than 25 milliseconds to process 3/4 of a second of audio. That's fast.
Very fast. Faster than the blink of an eye. This rapid response time is fundamental for practical real-time edge applications, ensuring that devices can react almost instantaneously to their environment. It makes interactions feel seamless and natural, not laggy.
Okay, let's bring it all together then. The big picture trade-off.
In summary, yes. This design makes a very deliberate and, I think, intelligent trade-off. They accept a modest increase in error rate, approximately 2% to 5% higher word error rate in their speech example, compared to more conventional, power-intensive floating point methods. However, this relatively small hit in accuracy is consciously exchanged for a system that offers significantly lower power consumption by an order of magnitude, a dramatically reduced memory footprint by orders of magnitude and parameter count, and better, lower latency. And crucially, as we discussed, it's not a fixed trade-off. If a specific application absolutely demands higher accuracy, the architecture provides the flexibility to tune it. You can increase the number of nodes per reservoir or perhaps the total number of reservoirs. Even with such adjustments to boost accuracy, the design philosophy ensures it would likely still achieve substantial power and memory savings compared to conventional solutions, making it a highly adaptable and efficient platform.
It's about choosing the right tool, or tuning the tool correctly, for the specific job and its constraints. And for many, many edge applications, ultra-low power and low latency are the absolute priorities.
Precisely. For always-on keyword spotting, simple command recognition, basic activity tracking, anomaly detection and sensors, this kind of extreme efficiency is exactly what's needed.
This has been a truly enlightening deep dive into some genuinely cutting-edge research. It's amazing stuff. We've seen how, by meticulously studying the brain's incredible efficiency, these researchers from the Indian Institute of Science have engineered a practical neuromorphic system. It cleverly uses a split reservoir architecture, enhanced by time multiplexing for hardware reuse. It couples this with on-the-fly binary weight generation, using LFSRs to slash memory needs. And it incorporates biologically inspired sensing like the neuromorphic cochlea model for audio. All of this combines beautifully to deliver ultra-low power, low latency, and low memory AI right at the edge, right on your devices.
It's a really elegant combination of ideas from neuroscience, computer science, and hardware engineering.
Absolutely. And the broader implications of this work are vast and incredibly exciting for the future of technology we interact with daily. This really paves the way for a new era for always-on smart wake-up modules in our devices. Think about it. Imagine your voice assistant waking up truly instantly with zero perceptible lag because it's always listening efficiently on the chip itself, consuming negligible power while waiting.
Getting rid of that slight, sometimes annoying delay.
Exactly. Or picture your smartwatch detecting specific activities, not just steps, but maybe recognizing if you're cycling, swimming, or even falling with remarkable accuracy, all without constantly draining its battery. Perhaps needing a charge only once a month instead of every single day.
That would change the usability of wearables dramatically.
Definitely. And think about specialized medical sensors. Implantable or wearable devices processing critical health data like ECG anomalies or glucose level trends in real time right on the device. This could provide immediate alerts without needing a constant, potentially privacy-compromising connection to the cloud.
Huge implications for personalized real-time healthcare.
What's also fascinating, and to mention in the paper, is that the same fundamental hardware architecture developed here, this time-multiplexed binary reservoir system, can likely be adapted to different sensor types beyond just audio and accelerometers, maybe image sensors, pressure sensors, chemical sensors. You just need the right feature extraction front end. This could significantly reduce development costs and accelerate innovation across entire industries, from smart homes and cities to industrial IoT and healthcare.
It provides a flexible, ultra-low power processing core.
Right. And if we look even further down the road, maybe push the boundaries a bit.
This work not only brings us closer to truly intelligent and practical edge devices that are feasible today, but it also strongly hints at a future where AI systems can actually learn on the device itself with minimal resources.
On-device learning, without needing the cloud for training.
Potentially, yes. The ability to perform multiplier-less operations, which is core to this design's efficiency, is also very attractive for implementing on-chip learning algorithms. Training often involves gradient calculations and weight updates, which can be complex. But if the core operations are just additions and shifts, maybe simpler, more efficient on-chip learning rules become feasible. This research points towards that possibility. It could fundamentally change how personal AI evolves, making our devices not just smart based on pre-trained models, but truly adaptive and intelligent, learning from their own unique experiences and environment without ever needing to send potentially sensitive data to the cloud for retraining.
Wow. Devices that learn and adapt on their own, privately.
It's a powerful vision. So here's a provocative thought, maybe something for you, our listeners, to mull over as you go about your day. What new capabilities, what entirely new forms of personalized private intelligence might unfold when every sensor we interact with in our homes, on our bodies, in our environment, has the ability to learn and adapt on its own, running efficiently on just a few milliwatts of power? What does that future look like?